As we've been talking about partial derivatives, we're talking about holding one variable constant so that we can just have one or two variables constant so that we can just have one input variable and create a function of one variable. And it may seem a little bit contrived. We're sort of doing that so that we can use what we already know from single variable calculus, so that we get a curve and we can draw a tangent line. But I want to point out that that's actually a very useful technique and skill that's used in the sciences all the time. I've got up on the board the ideal gas law. Some of you are going to be familiar with it, not something you're responsible for in and of itself. The formula would be given. But here, P stands for pressure, T stands for temperature, and V stands for volume. All of these are properties of a gas. K is going to be a constant, and different gases will have different constants, but if I'm studying one particular gas, there will be a constant associated with that gas. Okay. And what scientists have discovered is that the pressure is proportional to the temperature, but inversely proportional to the volume. In other words, if I increase the temperature, that's going to also increase the pressure of the gas. If I increase the volume, the space that the gas has to be gas in, that's going to decrease the pressure, okay? In such a way that we get an equation that looks something like this. Now, scientists aren't born just knowing the ideal gas law. These properties of the natural world are discovered through experiment. And when you go into a lab and you've got three variables, pressure, temperature, and volume, and you're suspicious that they might be related to each other, you don't start changing all of them and just sitting back and seeing what happens. What you do is you say, okay, I want to study the effect of one on the other. So, if I want to study how temperature affects pressure, I'm going to hold the volume constant. And when I hold the volume constant, then what I'm going to do is I'm going to change the temperature. So at a certain temperature, I'll measure the pressure. I'll increase the temperature, I'll measure the pressure again. And if the pressure is changed, because the only thing I changed was the temperature, I can reasonably assume that the reason the pressure changed was because I changed the temperature. Then when I want to see how volume affects the pressure, I'll hold the temperature constant and change the volume. Okay. So what we're doing mathematically when we hold all but one of the input variables constant is we're doing what scientists do experimentally. They say, okay, I'm going to treat, this is my output. This is the thing that I'm going to measure after I've done whatever I'm doing. For the input variables, I'm going to control all but one of them so that I can see, changing just this one thing, how does that affect, in this case, the pressure. Okay. And so if I were to take a look at the partial derivative of pressure with respect to temperature, that would be the sort of thing that you would measure in an experiment where you were holding the volume constant. And of course, if the volume is constant, then we've got K is constant, V is constant, and then T is my variable. So I would just get this constant multiple of my variable. The derivative is that constant. Okay. On the other hand, if I took the partial derivative of pressure with respect to volume, I'm just going to make a note that that's the partial with respect to V of, I'm going to rewrite this as KT times V to the negative 1. Okay, so rewrite it as a negative exponent. K and T are constants, so I'm just going to get negative KT V to the negative 2, or negative KT, over V squared. Okay. But I think thinking of the way scientists do experiments really highlights that this notion of let's keep everything except one variable one input variable constant and measure its effect on the output variable, that really is the mindset you want to have if you're going into a lab doing any sort of an experiment.